So 30th is the Wednesday class, and then there we should have 1.5 hours of interaction on this. Vinod, you have noted, right? And you should send one email to everybody. Great. So today we are going to really start a very exciting, topic. This is actually connected. Some of you who did not participate in the last class, please go through the video lecture, because the background for this class was set in the last class. So essentially, we are going to discuss about a few landmark papers. And we are going to see how you bring in those wisdom and knowledge that you have acquired for different types of forces, like the surface tension force, like the van der Waals forces, all these wisdom, and we will add electric field and magnetic field. How do you bring in all these aspects into the colloidal domain for the modeling of different types of systems, right? And these are some of the very, very landmark works. So please be attentive, okay? There's a fun associated with that. You will not get the fun, and make it more interactive. I will be very happy, in this situation, if you interact and if you start asking questions at different places when I stop, or just to stop me whenever you feel that you're not understanding what am I saying, because this is where things will be built, the foundation will be built. And then from this onwards, if you don't understand, things will be difficult. My slides are visible, right? Somebody confirms.
Yes, sir.
Yeah, thank you. So I ask you a very simple question. When you have a wall and you put a coating, say suppose you have a wall, okay, and you want to put a coating on top of that. What is the purpose of putting a coating on the wall? Why do you coat a wall? Why do you paint a wall? Is there a necessity? What are the different purposes of painting a wall? बताइए, जल्दी से बताइए. Don't wait for others to respond. What is the purpose of coating a wall? What is the purpose of painting a wall?
Sir, is it to make the smooth?
Number one, it to make smoother. Then what are the other purposes?
For decoration, like we want to add colors.
Aesthetics, right?
Aesthetics.
Then
also nowadays some antibacterial, these type of paints have come out. So
yes, you should first give the scientific reason, right? Aesthetic comes later. What is the scientific reason of providing a coating on a surface? No idea. Nobody knows. Why do you coat? So why do you paint? What is the main reason we put coating on a surface? So it is to protect the surface, right? See, first reason is to protect the surface, correct? Am I correct? All of you agree with me? To protect the surface, correct? That is the first purpose. Now, question is that how thick, then I'm asking, say, suppose I want to protect a surface, how thick should be the coating? What are the factors that decide this coating thickness? Should it be very thick or should it be very thin? What is your opinion as an engineer? All of you are engineers now. So as an opinion, if I ask you what?
The sensitivity of this surface.
Sensitivity means?
So means how it can tolerate some disturbance like external agents.
How thick will my, see, your boss will be asking you a very simple question. How thick will be my coating? Why he is asking this question to you? Any idea? When you go and go for a coating business, no? So
for cost purpose?
Yes. He's asking to estimate how many, if you are putting thicker, then you require more more amount of paint. Whereas if you want thinner, then you will require less amount. And that actually is the main issue first. What is the cost to the coating, right? So if cost is one of the factors, then what should you do? Will it go for thicker or thinner?
Sir, thinner.
Thinner is better, right? Now question is how thin? So you first get the reason why coatings are thin. First you get why coating is necessary. This is what we discussed in the beginning, that coating, if you don't put coating, then what happens? Then first, your surface will corrode. Like somebody mentioned about antibacterial, right? The main issue is that, say, suppose if it is an iron material, if you don't coat it, it will be rusted. Right? If you have the civil structures, they will catch up what? They will catch up, humidity. There will be fungal growth, bacterial growth, and all these things, which is going to destroy the civil structure, right? Now, coating is essential. That is, I have to do it. But then when I do coating, it is adding additional cost to the product. Now that cost has to be minimized. That means my thickness should be minimum. So you get two purposes. One, the coating is necessary. Second is the coating has to be thin. It should not be very thick. Until or unless you have a lot of money to waste. Now, once you are done with these two purposes, then question is how thin the coating will be. What does the thing that decides that what should be the thickness of the coating? Let me ask you a practical question. Whatever typical coatings you see in front of yourself, what is the typical thickness of the coatings? Have any idea? What is your guess? Is it millimeter? Is it meter? Is it centimeter? Is it micrometer? Is it nanometer? What is the thickness of coating typically?
Millimeter, sir.
Millimeter is about say 1 unit of your scale. Have you seen any coating of that thickness? Yes? Or is it thinner than that? Any idea?
Micrometer.
Yes. So either it is micrometer or less, because you cannot estimate, right? It is thinner than millimeter, that is for sure. Right? So it is either micrometer or less. So now question is whether it is micrometer. If you are putting it, then whether you should be putting micrometer or nanometer. What will be your choice based on the cost?
So nanometer.
Nanometer, or even a single layer, like we are talking about graphene, right? Say that is about 2 nanometer, correct? So lesser and cheaper is the material. Your purpose is solved, that you have protected. You put colors and all, like dyes, dye molecules, and all these things, and then you are through. Right now, then what is the game? How thin you can go? So I tell you now a story with this background that, say, suppose if you have a micron thick film. Right. So what you see in front of the walls and all these things, you will find that they are all micron thick. Right. See, essentially, most of these are polymers. And these polymers are, you are basically giving a coating of a polymer on top of a surface. Right. So people started doing experiments. And it's a very simple model that, you have a spin coater. This is a spin coater. So spin coaters essentially have a chuck, okay, which is rotating, and then you have a vacuum, and then you put a substrate, and you put a polymer solution on top of that, and then you spin at a very high speed. So the centripetal force, it spreads the liquid on the surface, forms a uniform film. Now that film, as you change the spin speed, as you change the polymer in the solution, the thickness of the layer you can control. You can go for micron to say suppose up to 5 nanometer film, you can coat using this technique called spin coating. So people thought that, let us coat films on a substrate, on a standard substrate, which is to be coated. So suppose this computer, right? On the computer, you have coated with some paint. You have this mobile phone. On the mobile phone, you have given a coating of paint in order to protect, right? Question is that how thin I can go, and the purpose is that thinner is and how cheap is the material, and how much thin I can go. So this actually adding to the cost. This is actually reducing the cost and adding to my profit. As a technology person, as an engineer, as a production house, this is actually adding to my profit, and it is going to the reduction of the cost. Right? So when people started reducing the thickness, say suppose if you coat a 10 nanometer film, you suddenly see that beyond 10 nanometer, you may see the continuous coatings or the kind of paintings that you see. Say suppose 1000 micron to say suppose 100 nanometer, you see all the surfaces are coated with coatings are continuous. I mean, there is no discontinuity. Then the coating hold good on the surface, right? But then as you go down the size, as you go down towards say suppose 40 nanometer and less, you start observing that say suppose if this is a solution, if this is a liquid, so these black spots are some of the holes that are forming. These black spots are over a period of, so you can see this is 770 seconds, this is 2270 seconds. So this is about an hour, right? This is about 2 hours. So as you progress, you will find this film will not hold, it is going to deviate. So this particular paper came in Nature Materials, I think 2003. Okay, this is the experimental image. This is the AFM image of a film which you have spin casted on top of a spin coater, and then you have just annealed it beyond its glass transition temperature so that flow becomes possible. It's in a fluidic domain. So you will find that a coating which is of very thin film thickness, it is going to disintegrate by forming some holes, and these holes they grow because now moment the hole is formed, you will find like this is the 2D simulation. When the hole is formed, this is not under equilibrium contact angle, so you can see the hole grows, and as the hole grows, there is a reinformation that is taking place, right? And then as as the hole grow to achieve the equilibrium contact angle, they form droplets. Although here the droplet did not form, right? Sorry. The droplet did not form, but you may see that the whole growth stage is here. So ideally, you will find later on, I will show some of the videos where, this is what is called, this particular process is called the dewating of a thin film. Okay. What do you mean? That, you were expecting this was supposed to form a continuous film. But then there's some reason because of that, this did not form the hole. This did not form a film, but this started forming the holes, and these holes they grew. These holes they coalesce, and they form a kind of like disintegrated film. Now, from here to here, the whole purpose of coating is lost. So essentially, this phenomena gave what? The manufacturers the lower limit. Okay, like say suppose if you go below 100 nanometer, the coating industry will not recommend you to coat anything less than 100 nanometer. Why? Because less than 100 nanometer, you may see this particular phenomena, which is called the dewating of thin film. Okay, and people have simulated the dewating of thin film, and they saw that it exactly happens like that Now, question is, what did they do in order to really see what is happening here? So this is a simulated picture taking into account all the forces. So here you see these are the hole formation. Okay, this is the place where the holes are forming, the holes are growing. Okay, then holes are coalescing. And then, these are the places where the polymer ribbons are there. And this is the place where the whole coalescence that has taken place, right? So essentially a picture which is very similar to the picture that you see here, that is reproduced. And then, you can really argue that, yes, this is one-to-one mapping. Now, how do we interpret theoretically? This particular experiment was first performed, I think, 1992 by Professor Gunter Reiter. He had a science publication, right? And then I think there were a flurry of physical regulators, science, nature that came up. Finally, in this particular paper only, they could summarize the whole reasons behind the experimental observation and the computational observations, but still there are a lot of issues that are not understood. So this is still an open problem. Why this is happening like this? And what is the reason behind such formation? I'm going to give you one of the hypotheses that people believe that which is the most probable reason for this activity or for this observation. Okay. Yeah. Any question you have up to this point?
Sir.
Go ahead.
So if this film is left alone only, then this hole starts forming. Means we don't need to do anything.
Nothing. You coat it, okay, and you leave it for 770 seconds. You just heat it up, but because if you just leave a polymer, that's a solid film. But if you just heat it to a glass transition temperature, then the fluidity appears. If you just heat up to a glass transition temperature, you will naturally see this you can do routinely in the laboratories. Okay. Yeah. What is the other question?
Sir, during this transition period, does the nature of the film or the liquid changes? So
no,
because of
it's the same material. Same material. It is a coating only. Material nature is not changing.
So why this phenomena happens, sir, here then?
What is your guess? See, we have been studying this, no? Say, suppose I have a surface. And I have a surface which has a surface tension of gamma S. And then I have a liquid, which is the surface tension of gamma L. So in which situation I will have a film? Gamma S should be what? Greater than gamma L, right? In that situation, I will have a film. And in which situation I have a droplet? In the situation when gamma S is less than gamma L?
Yes, sir.
Right. So I will have a droplet. So this film, say suppose I have taken a surface which is low energy. I've taken a surface which is of low energy, and I'm trying to coat a film which is of high energy, right? High surface energy. So what do I expect to happen? So initially it will form a film, correct? And then after a point, what will happen? After a point, what will happen? This film will break into pieces. First, it will form holes. These holes will grow. They will coalesce, and then they will get converted into droplet. Okay, so this phenomena is called the weighting of a surface, while this particular phenomena is called the deweighting of a surface. Right, but there is something more into it. Okay, what is that something more? I'll come to that. The other very interesting experiment, this is again 2001 Nature paper. Other very interesting experiment is that, so suppose you have the same film and you have sandwiched this between two electrodes, right? If you have a electrode and say suppose this is a polymer, and if you have another electrode on top of that, say suppose you have two electrodes and in between you have a polymer. and then you have applied an electric field through these electrodes. Okay, so suppose this is cathode, this is anode, and this is a polymer, means this is a electrically insulator, right? What is this particular configuration called? Anybody has any idea? What is this called? If you have an insulator sandwiched between the two electrodes. Huh?
Die capacitor, sir.
Capacitor. What is the name of this capacitor?
Parallel plate capacitor.
Parallel plate capacitor, right? So this is called a parallel plate capacitor. So I'm just changing the configuration a little bit. Rather than keeping only polymer, I am keeping two dielectric layers. Air is there, and then there is this polymer solution, and then I have two electrodes. And I'm applying an electric field. This is again, you can call this as a parallel plate capacitor. What is the beauty of parallel plate capacitor? That you can understand that if this is positively charged, then say this is plus, right? So this place it will be minus. So essentially these bound charges are getting separated. This is plus, okay? This is minus, right? So this is again plus. So there will be a kind of polarization will happen, which is by the electrode, the way you have applied the field. Now, when you create such configuration, say you can understand that when you apply the electric field, there is a charge separation and charge accumulation that has taken place at the interface, right? So immediately you will see this is the top view. You are looking from the microscope from the top. This is a glass electrode. Okay, you are putting up an objective here, right? And you are observing from here, right? So this is the top view. So initially you will see undulations like this. Then you will see some columns will form like that, and then you will see beautiful columns. This film is getting deformed into say this sort of hexagonal ordering, where this is the central column and these are the columns which are surrounded. So if you take every column, you will find a kind of hexagonal ordering around that column. Right. So I'm just bringing in about 10-15 papers. Number one phenomena is the deviating phenomena, and number two phenomena is the column formation phenomena, where you can create, these are called the micro patterns or nano patterns, microstructures or nanostructures. What is the advantage when you are doing, say you are having a surface, right? Again, the same method is same here. You are taking a substrate. Essentially, rather than taking a substrate, you are taking an electrode. On top of that, you are coating the polymer film. You are bringing in another electrode. Okay. Say this oblique one is creating columns in a gradient manner. So where the gap is less, first the columns are forming and then going like that. If it is parallel plate, then you are able to see columns of equal size. Okay. So essentially, what you are doing, you are taking a flat surface, right? And this flat surface is converted into either a surface full of droplets or a surface full of columns. And you can imagine that this pattern surface will have very high surface to volume ratio, very high surface area per unit mass. Why? Because you have deformed the same surface into multiple structures, right? So this can be very good, catalyst. This can be very good. These are the ways you generate super hydrophobicity. So if it is a hydrophobic surface, if you pattern them, it will become more hydrophobic. If you put hierarchical structures, that will become super hydrophobic. So patterning of a polymeric surface, patterning of a surface, have become a kind of a very important activity. Why? Because it gives you more surface area. More surface area means more adhesive properties. More adhesive properties means more activity on the surface in terms of catalytic activity, in terms of other activities. Okay. So now let us weave the theories that we have learned around these two problems. Like whatever we have learned in terms of the governing equations, boundary conditions, like whatever the forces that we have learned, how do we really bring in the knowledge in order to really describe the system, right? So in order to do that, first we derive an equation which is called the famous thin film equation. So what is the problem here? In both the situations, I have a problem where, what am I doing? I'm having a surface, and on top of that, I have a film. Correct? And what I do, I take a differential volume element of that film in 2D only. 3D will be trivial after we understand that 2D. There, I say that the thickness of the film is h, which is a function of x and t. Why do I say x and t? H is this height and this is x, right? And then what I do, I perform a mass balance. And this particular gap has a thickness of what? This particular gap has a thickness of dx. Okay. So in this differential element, what is the amount of mass that is coming in? So I have this is x and I have this is x plus dx, right? What is the mass that is coming in x? It is u is the velocity, dz is the height, u into dz, and I'm considering, the element that is perpendicular to the plane of the paper is 1. So this is meter per second, this is meter, and this is also meter. So this is meter cube per second. This is the volumetric flow rate. Density I ignore. Rho is always there. So this becomes what? This is per unit time the amount of mass that has come in through x. And the same is this I'm integrating over 0 to h for dz. And the same is whatever is going out. This is my mass that is going out. Now this is nothing but, what is the change here? Change here is h into dx, right? This is the height and this is the x. So del t of h dx, that means the change in the height in locally at every place. That is nothing but what? The u dz 0 to 8 at x and u dz 0 to h at x plus dx. Right? This is the mass balance across the differential volume element, which I simplify to get del h by del t is equal to del x of 0 to h u dz equal to 0. Right? Just I have simplified this. These things are taken on the left hand side. Now what you do, you apply this Lifshitz rule. This is a variational principle that if you have del x of u dz h1 to h2, you can write h1 to h2 del u del x del z, u at h2 del h2 del x minus u at. This is an identity that is available. Right? If you enforce this identity here, you are going to expand this into 3 parts. One is this part, one is this part, and the other is this part. Right? What is this part? What is this part? You see that h1 to h2, that means 0 to h, right? So here you are converting it to 0 to h. Del u by del x into delta z, right? Now what is this part? uh to del h to del x. So uh into del h by del x. Your h2 is h. Whereas uh1 del h1 by del x. u0 into del h by del x. So u0, you know that at this particular point it is no slip. This is cancelled. And then you have del u by del x into del z. Del u by del x is what? From continuity, del u by del x plus del w by del z is equal to 0. So you can write del u by del x equal to minus del w by del z. So what you do, you replace this del u by del x with minus del w by del z. Del z goes. So this becomes wh minus w0. Now w0 is what? W0 is equal to 0 because of the impermeability condition. So overall, you get an equation which says that for a film like this, you have the expression, if you do a mass balance, del h by del t plus u into del h by del x is equal to w. Or you may write a little bit smarter manner, u del H by del T plus u at H into del H by del X is equal to W at H. So this is the famous thin film equation. What people are saying that, so suppose if I want to capture the dynamics of this height of the film, first what I do a kind of mass balance in order to see, like, how this height is changing, when the u is the x directional velocity and w is the z directional velocity. Okay, any question up to this point?
Sir, can you please explain this del T HDX? Sir, that is mass accumulation. What is that, sir?
Yes. Very nice. So this is the amount of mass that is coming in through this phase, right? And this is the amount of mass that is going out these two phases. Now, if that is the case, so what is the change in the mass? So h is the height, dx is the weight, and then you have the perpendicular, that is 1. So that is the total volume that you have, the del T, and then if you multiply rho, that means it is mass, right? Mass flow.
Okay, sir.
Clear? So what is the change? You are asking in a question at a location at a particular point. What are those points? These points. Say when I'm looking at it, I'm looking at this every point, right? Here. So if I want to know what is this h is a function of x and t. So it is said that if you solve the equation del h by del t, okay, plus uh del h by del x equal to wh. If you solve this equation, then you are able to get the contour of this. And essentially, exactly, you are doing it here. You are doing it here, right? You are tracking what is the change in the height with respect to time. So this is 770 seconds. This is 2270 seconds. This is 4000, 6000. So as things are changing, you see what is changing? The height is changing. And tracking the height, you are able to tell what's going on here. If you know UH, if you know WH, UN force, you solve for how is the change in the H in the X, and then you look for what is the H. So one is the space derivative and the other is the time derivative. Could I answer your question?
Yes, sir.
Great. Now, how do we approach? Simple. I have a film, I have a substrate, and what is the equation that is applicable here? What is the equation that is applicable here? We have done so many times. Midsem exam is done. So for the liquid, which equation will be valid? Jaldi se batao.
Navier-Stokes equation.
Yes. So continuity equation, and I am doing two-dimensional Navier-Stokes equations, right? But here you see that I'm adding a mystery parameter, which is called phi. Rest is straightforward, right? This you know that this is the local acceleration, this is the convective acceleration, this is the viscous term, and this is the pressure term, but I am adding a surprise term here, which is phi. And this phi is what? This phi, in this situation, it is the van der Waals forces. In this situation, it is the electric field. It can be any force. It can be a body force. It can be gravitational force. It can be magnetic field. It can be electric field. It can be van der Waals forces. You can bring in any description here for this phi. You just add it like that, and then you develop the formulation. Okay. So I'm saying that this is nothing but the game between the body force and the surface forces under the framework of the Navier-Stokes equations. You have done it already, correct? And then I enforce the boundary conditions, which you already know, u equal to w equal to 0. I have already enforced while deriving this. And then I'm doing a very interesting thing here. At the interface, this requires a little bit of attention. How am I doing that? I'm doing this way. That I'm saying that, say, suppose this is my surface and suppose this is my fill. So at this particular point, and you have to understand that this is not a flat boundary. This is a moving boundary. So you will learn how to enforce a moving down boundary condition. Okay, a boundary condition that is associated with the moving boundary. So how do I do a kind of moving boundary? So what I do a, say suppose this is air. Okay, so I say this is FA, and you know this is the liquid. So suppose this is FL. So for an equilibration condition, if A should be equal to FL, you know, there should be a force balance all across this. So how do I obtain the force balance? What I do, I resolve this force into normal component. Okay, the normal component, and I resolve this into the tangential component. Normal with respect to this, tangential with respect to that. So FA will have a normal and tangential component. FL will have a normal and tangential component. Now what I do, I balance the normal and I balance the tangential. I balance the normal to normal and I balance the tangential to tangential. How do I do that? Let us see. So I say that at this particular point, how do I get a normal? Anybody can tell me, how do I get a normal here? This normal vector, how do I get? If h is the height, what is my normal? Anybody has idea? What is my normal? How do I get normal? Gradient of h divided by modulus of gradient of h. Okay, this is my normal. Any place, any point you want to get a normal for any curved surface. Any curved surface, if you really want to get the normal at a particular point, what you need to do, you need to define a scalar phi. Here the scalar is h. So normal is the gradient of phi divided by the modulus of the gradient of phi, which is written here. This is the normal, and the perpendicular to the normal is the tangent. So n and t you can obviously get from what? The height. Whenever you know the h, you get the n and t. Okay, by the way, this n and t expression, no, submit as an assignment. Okay, from here. All of you should do it. Okay, so how do I get n? The normal vector. A normal vector I get gradient of phi divided by modulus of the gradient of phi. So here it will be gradient of h divided by the modulus of the gradient of h. Okay. Right. Now, how do I do the normal and tangential balance at the interface? So what is the normal balance here? What is the normal balance here? So suppose I have a curved surface, right? What I say that, say anybody remembers what is the Young-Laplace equation? What is the Young-Laplace equation? Anybody remembers? If you have a curved surface, if you have pressure here P1, if you have pressure here P2, then what is the Young-Laplace equation? जल्दी बताओ.
P2 minus P1 equals P2 minus P1 equals to one gamma into 1 by R1 plus 1 by R2.
How do I write 1 by R1 plus 1 by R2 for an arbitrary surface? Gamma into kappa, right? Where kappa is the mean curvature. What is kappa? Gamma into divergence of m, right? Am I correct? This R1 and R2 is nothing but divergence of n, right? पढ़ा है, भूल गया है. Laplace equation derive करने के टाइम में दिखाया है इसको. Expression भी दे दिया है. शायद assignment देना भूल गया था. So this R1 and R2 are nothing but the mean curvature, correct? That mean curvature is defined as kappa. Kappa is nothing but divergence of n, and n is what? N is again the gradient of age divided by the modulus of gradient of age. तो देखो right hand side तुम्हारा clear हो गया यहाँ पे. Now what is the left hand side? Left hand side you see that earlier when we went for this delta P, no, we did not worry about what is the fluid here, what is the fluid here. We just worried about what is the thermodynamic pressure there. Assuming that the interface it's a line interface, and then we were not really worried about what are the fluids that are there across the interface. Okay, but right now we are bringing in the concept of the fluid, and that's the reason why we are doing what we are saying, that the stress, okay, the deviatory plus the principal stress, that is sigma, right? So suppose if you have sigma, how many components are there for sigma? Sigma is a tensor, right? How many components are there for sigma for a fluid? How many components are there? There are how many components? Jaldi se batao.
9 components.
There are 9 components. Now say if I take n dot sigma, this how many components are there? N is a vector, right? If you take a projection of sigma towards n, then how many components are there? जल्दी से बताओ. वेक्टर के साथ एक टेंसर का डॉट प्रोडक्ट लेने से कितना कंपोनेंट रहता है? भूल गए? कितना प्रैक्टिस किया?
Vector.
It will be a vector.
हाँ, so there'll be 3 components, correct? And then n dot sigma dot n. How many components?
So 3 only, sir.
3.
So that is a scalar, right? N dot sigma. Or
Which one is a scalar?
N dot sigma is a vector. Then
Hmm.
sir, I'm getting confused. Sir.
Why confusion? Why there is a confusion? कितनी बार करवाया है? This is the reason why we spend so much of time there. Where is the confusion? You can't see this, it's very simple, no? NKEK dot sigma ij EIJ dot NMEM EKEI delta KI EJEM delta JM NK sigma ij NM. So this is what?
Sir, only one value.
So this is a scalar, right?
Scalar.
If you take 2 dot products with a tensor, it's a scalar. 1 dot product it's a vector, and this is the tensor. What am I doing here actually when I'm doing this operation? What am I doing? I'm doing what? So sigma, that, it has got how many? 9 components, right? It has got 9 components, right? Now when I'm taking sigma dot n, that means what are the components that I'm taking? Or n dot sigma. Which are the ones that are prevalent here? If I take n dot sigma, among these 9, what are the 3 remaining? जल्दी से बताओ. ये वाला, ये वाला, ये वाला. Because normal is in this direction, right? If n has this direction, then when I take n dot sigma, these three survives. Essentially, you are aligning towards the normal, the entire sigma, that is the projection. Now, when you take another n here, then which one survives? What is the direction that survives? This will be what? In which direction? Or this will be magnitude towards what? You know, if you take two n dot products, it will be this one, right? ZZ1. Correct. Now, if I go for n dot sigma dot t, then it will be in which direction? It will be in this direction, right? Rather, it will be the one which is here, this one, which is the tangential component. Correct. So if you look at here, so what I do, I say that there is a force equilibrium across the interface. Now the normal one is nothing but this is the normal that is in the gas, normal force that is in the gas. I'm writing in terms of the stress because we have already proven that delta P is equal to gamma kappa. I am just expanding the scope of this P to what? I'm writing n dot sigma film dot n minus n dot sigma air dot n is equal to gamma kappa. This is nothing but the extension of the Young-Laplace equation with all hydrodynamic forces, viscosity, these, that, body force embedded inside it. That the difference between the normal forces across the interface is equal to the mean curvature into gamma. This we have proven from the thermodynamics. So take care of the normal, and tangential is what? Very straightforward. N dot sigma dot t is equal to, for film, is equal to n dot sigma dot t for air. So what is the essential conclusion from here? That you have a thin film. You have a thin film. So what are the equations? See, del u by del t plus u del u del z plus w del u u del u del z plus u del u del x plus w del u del z is equal to minus. I'm just putting a kind of p plus phi. Phi is the surprise force into what? I just put a rho here so that I don't get into trouble. Mu into del square u by del x square plus del square u by del z square. This is my x momentum. Rho into del w by del t plus u into del w by del x plus w into del w by del z is equal to minus del of p plus phi into del z plus mu into del square w by del x square plus del square w by del z square. Then I have del u by del x plus del w by del z equal to 0. I now draw, the boundary condition here, u equal to z equal to u equal to w equal to 0 at z equal to 0. At z equal to 0, at z equal to h. I have got three boundary conditions. Number one, del h by del t plus u del h by del x is equal to w. These are again u at h, del h by del x, it is equal to w by h. Number two is n dot sigma film dot n minus n dot sigma air dot n is equal to gamma kappa. And number three is that n dot sigma film dot t is equal to n dot sigma air dot t. Okay, where kappa is equal to what? Kappa is equal to divergence of n. Any confusion in this framework? Is it clear? How am I getting into this thin film dynamics? Any question? जल्दी से बताओ, नहीं तो गाड़ी निकल जाएगी अभी. It's as simple as that. What the way I'm writing, okay? Okay, let us progress. Now, so if I expand this, so this is again, I mean, I'm just giving you an assignment that you know what is n, right? N is this, T is this. Expression is given. You know what is sigma also, right? For a Newtonian film. Gradient of V transpose, right? If you put in all the parameters, so the expression for your normal stress balance will come like this. Okay, and the expression for normal stress balance like this, for this one, you will get something like this. Okay, and expression for the tangential stress balance will come like this. Okay, so first prove these things. You submit that n dot sigma dot t and n dot sigma dot n is going to give you this and this. These are the two expressions that you should prove. Right? Submit it. That what is the expression for the normal stress balance? How do you get this from this? How do you get this from this? And from this, how do you get this part? Okay, prove it. Essentially, you will get this part. This part you will get from the tangential stress balance. Okay, and from the normal stress balance, you will get this part. Just leave this epsilons away, when you prove it. Now what I do, you tell me this is solvable or not. This particular system is solvable or not. Can you solve this system? Is it possible to solve analytically this system? The answer is no. You cannot solve it. It's a very complicated system. You need a lot of mathematical skills, even in order to really get a part of solution of that, right? But then if you do a very smart analysis, you will be able to really obtain the solution, right? How do you do that? So say suppose you have a phenomena that is happening like this, correct? So what is the order of magnitude in terms of time? Is it large or small? Is it large time or small time? What is your take? Say suppose you are watching that the holes are forming at about 2 hours, right? Is it a large time or small time? What is your take here? Any idea? Any idea? Any idea you have? Is it considerable? Is it large? Is it small? Are you willing to do this experiment for 2 hours? Yes, no. Now, second question that I ask, that what is the length scale? Okay, so here, what we are trying to do, we are trying to set up a kind of scale for every system, every particular parameter, and identify that which parameter is large and which parameter is small. Correct? And what is our benchmark? The benchmark I am setting the height of the film. Okay, which I say that I consider to be about 1. That is my scale. Now say suppose if I say the film thickness is my 1, then what is x? X is large or small? X is large or small? If z remains to be my benchmark, then x compared to that x is large or small? if Z remains to be my benchmark, X is large or small? In a film, in a thin film situation, sorry, in a thin film situation, say suppose if we have a film, it's a very thin film you have quoted, right? So now if you say this to be 1, then this is how much? 1, 10, 100, 1000, how much is the X? Is it large or small?
Large.
Large. So that's why I say that in order to have an equivalent parameter to Z, what I do, I say that X bar is nothing but epsilon X. X is large, I put a order of magnitude epsilon so that it becomes equivalent to Z. And now the time that you see, whether it is large or small, why there is a silence? Is it large, small? What type? Say suppose what is your standard time scale of a process? Say if something is very small, things will happen faster or slower. What do you anticipate? Whether things will happen faster or slower. If the process becomes smaller, whether things will happen faster or faster or slower.
Faster.
Faster, sir.
It will be a faster process, right? So
Yes, sir.
now, in order to make the process faster, you say that if T is my time scale, so I say that T bar, which is my time scale for this particular thing, which is equivalent to epsilon T. Okay. Now, this also you can come from, say, del U by del X plus del W by del Z, right? So you know that Z is of the order of 1, right? But W is, this velocity is very small because your velocity is essentially in the X direction. So W you can consider to be epsilon. Okay. Now X you can consider U to be 1. If that is the case, then what will be X? If you really need to maintain mass balance, what should be X?
Around 1.
1. Then mass balance will not be there. What should be X here? Anybody? What should be X? If W is small, if Z is 1, if U is 1, what should be X?
1 by epsilon.
Fantastic. So you can see this is what I have enforced here. X is equal to what? X bar by epsilon. Very tricky, but then once you understand, it's very interesting. Okay, same for time. So I have set up a set of parameters. Now let us make it less clumsy. Let us go back to this. So here you know that W is epsilon. Z is equivalent to 1, U is equivalent to 1, X is equivalent to 1 by epsilon, right? And then, what I do, I enforce this and I assume that P pressure, because I am bringing in the forces here, I assume that P is large. 1 by epsilon, and I just bring in to the set of equations, which is del U by del T U, del U, del X, W, this. In this, I just start enforcing. So what did I say? I replace T, which is my time scale, with what? T by epsilon to magnify the time scale. This is what I did here for a faster rate, right? For a smaller things will be faster. So T is replaced by T by epsilon. Now U is what? U is 1. This U is 1, but X, for X I will have epsilon because X is 1 by epsilon. Now W already has epsilon, so this epsilon is coming from there. U is 1, Z is 1, so this remains same. So epsilon comes here. Now P has 1 by epsilon, phi has 1 by epsilon. X is what? This P has 1 by epsilon and sorry. P and phi both has 1 by epsilon, right? That is very high. And X also has 1 by epsilon. So epsilon will go up here. You get the point, right? P and phi has 1 by epsilon and X has 1 by epsilon. Since X is in the denominator, it will go epsilon by 1. So epsilon will cancel out. You will see that there is no epsilon that will be surviving. For X, there are 2 epsilon. That's why you are getting epsilon square. U is of the order of 1. So this will be epsilon square. Z is 1, U is 1. So this remain as is. Z is 1, U is 1. This remain as is. So if I just enforce this scaling, I'm going to get an order of magnitude where this is epsilon, this is epsilon, this is epsilon. This has no epsilon. This is epsilon square, very small. And these two terms, which is the leading order terms. Okay, I'm just dropping. Epsilon is a signature of which term will be a small term for me to ignore. Same, let us start looking at it. This is again, W is epsilon and T is 1 by epsilon. So this is epsilon square. U is 1. X is 1 by epsilon. W is epsilon. This is epsilon square. W is epsilon. W is epsilon. Again epsilon square. So all these 3 terms will have epsilon square. What will be the order of magnitude of this one? So this is 1 by epsilon. Z is 1. So this is 1 by epsilon. What will be this one? Epsilon and epsilon square. That means epsilon cube. Z is 1 and epsilon is there. So this will be epsilon. So if you look at all the terms, you will find that this is epsilon square, very small. This is 1 by epsilon. This is very large. And these two. So this is the leading order term in this particular equation. Okay. Now, similarly, U enforce del U by del U and 1. U is 1, Z is 1. So there is no coefficient. W is epsilon. This is 1 by epsilon. So epsilon square. Del square H by del X square. This is epsilon square. Okay. Del H, del X, del W, del Z. This is epsilon into epsilon. So this is again epsilon square. So you will find, one can push these terms at the same time in the normal balance. We can push these terms. Now, if I just remove all the epsilon related terms, you see, I get a very simple equation. Mu del square U by del Z square is equal to del P by del Z, del P plus phi by del X, and del P by del Z equal to 0, where P is a function of Z. This I'll come. So essentially, if I just start accumulating all the things which are irrespective of the epsilon terms, I will get a set of equation which will look like this. Which will look like this, that mu into del square U by del Z square is equal to del of P plus phi by del X. Now P plus phi, small p plus small phi, I call as capital P, which is equal to del P by del X. This is my X momentum equation. Okay. Then I will have del P by del Z is equal to 0, which is my Z momentum equation. Then I will have del U by del X plus del W by del Z is equal to 0. This is my continuity equation. Okay. Then I will have del U by del Z is equal to 0, which is my tangential valence equation. That is at Z equal to H, del U by del Z equal to 0. This is my tangential valence equation. And then I will have minus P plus P is equal to gamma into del square H by del X square, right? This will be my normal balance equation. Okay, and then I will have del H by del T. This is at Z equal to H. I will have del h by del t plus u at h equal to into del h by del x is equal to w at h. These are all at z equal to h, and I will have the set of equation. The other boundary condition will be at z equal to 0, u equal to w equal to 0. So essentially, you may see this set of equations are obtained here. As I go, x momentum gives me this equation, z momentum gives me this equation. This is my continuity equation. This is my tangential stress balance, and this is my normal stress balance, and this is my kinematic equation. So the complicated set of equations with an order of magnitude analysis, you are able to reduce into a set of equations. Now this is manageable. And this is true for what? Incompressible Newtonian thin liquid film. Any questions up to this point? A lot of hard work. Any
Hello,
doubts?
sir.
Yeah.
Sir, why we are considering slower reaction?
Where did we consider slower?
T equal to 1 by epsilon we are taking.
And that means large,
Time is large, it means rate of
I am
reaction.
replacing t, this t. See, the time that I'm considering, the new time that I'm considering, that is epsilon t, right?
Oh, okay, sir.
This t was my original time. Okay. Now I'm enforcing t by epsilon, correct? This t is coming here. So I'm looking for a faster situation rather than a slower one.
Yes.
Okay. Yeah. Any other question? Now, if you look at this del p by del z equal to 0, which is the z momentum equation, this tells that p is not a function of z. Is not a function of z. So what will happen to mu del square u by del z square? Equal to del p by del x, right? We can call it as a px or c1. So u equal to what? C1 z square plus C2 z. Let me do it. The space is very small. So I have an equation which is del p by del z equal to 0. This gives me what? P is not a function of z, right? So mu del square u by del z square is equal to px, which I consider to be constant because it's not a function of z, c1. So mu becomes, so u becomes, I can write c1 z square plus c2 z plus c3. C1 by mu can be, px by mu can be derived as a constant c1. So u is equal to c1 z square plus c2 z plus c3. Now what is del u by del x? C is a function of x. C is not a function of z, but c is a function of x. So it will become c1x z square plus c2x z plus c3x, right? Now this is equal to what? Minus del w by del z, enforcing continuity, c1x z square plus c2x z plus c3. So what is w? Minus w is equal to c1x z cubed by 3 plus c2x z square by 2 plus c3x z plus c4. Now what is my continuity equation? Del h by del t, u at h, del h by del x equal to w at h. So what is my u at h? Del h by del t. What is my u at h? Is c1 h square plus c2 h plus c3 into del h by del x plus is equal to what? W at h. That means c1x h cubed by 3 plus c2x h square by 2 plus c3x h plus c4. Now at z equal to 0, u equal to 0, right? So what happens to c3? This is one boundary condition, right? At Z equal to 0, U equal to 0. What happens to C3? Jaldi
Zero.
batao. Very good, 0. This is 0, right? So at Z equal to 0, W equal to 0, right? So what happens to C4?
0 again.
0, right? Now 2 gone, you have to get how many? C1, C2, C3, C4. You know, how many remaining? C1, C3, C4 gone. You need to know C1 and C2. You know del U at Z equal to H, del U by del Z equal to 0. Correct? So U is this. So what is del U by del Z? Del U by del Z is 0 equal to 2C1Z plus C2, right? So at Z equal to 0, del U by del Z equal to 0. That means C2 equal to what?
But it is Z equal to H.
Z equal to H, yeah. So C2
C2 will be minus 2C1H.
2C1H, correct? So C2 you have obtained. And then you need C1. C1 you will get from where? C1 you will get from the normal stress balance, that is from, so you can just, you know, now check up. So you can understand that all the constants can be obtained. You know, I think in the next page it is given. So this is the equation. So this is the one, you know, this is done in a different way. This is U, this is W. Now you bring into, you replace U and W at H. Okay, then you enforce the boundary condition, right? And then once you enforce, this is your normal stress balance. Okay, you enforce all the boundary condition, what you obtain. This is the famous thin film equation you obtain. Right? So how many equations are there? What type of equation is this first? What type of equation is this? It's a ODE, PT, algebraic equation. What type of equation is this?
The PD.
PT, right? What is the independent variable? What is the dependent variable?
T and X are independent.
Huh?
T, X are independent.
X and T are independent variables, right? So H is a, so we started with the assumption that H is a function of X and T, right? So X and T are independent variable, H is a dependent variable, right? So there is a linear nonlinear equation.
A linear.
Inside class.
No, sir. X is a non-linear. It is.
How come?
Theory.
What is the nonlinearity? Source of?
Sir, H cube del X term is there.
Very nice. Very nice. H cube is the source of nonlinearity. What is the order of the equation?
Sub order would be So, sir, I'm a bit confused with order and degree, sir, actually.
Order
First
is the
order with respect to time and second order with respect to space.
first order with respect to time is correct, but is it second order with respect to space?
Third order it is.
Huh? What is the order? Repeat. कितना ऑर्डर है बाबा? दिख नहीं रहा है, सीधा तो दिख रहा है.
Sir, 4.
Yes, fourth order nonlinear equation, fourth order in space and first order in time. ठीक है? Rewrite this. No, assignment. This is another assignment. So now you have, now this is this particular simulation is the solution of that equation. Okay. This is that equation. Correct. I will come to this a little later. Now this is another interesting way of like analytically analyzing what's going on in this equation. Right now, we are not going to attempt that. But we are going to attempt that, say, suppose if it is Newtonian, we went for this equation, right? Elastic, the framework remains same. Only difference is that here we are using this U is nothing but this is displacement rather than velocity. Okay, and this is the Hookean elastic framework. This is the continuity equation. These are the momentum equations. These are the normal tangential stress balance. Only thing that U and W becomes the displacement field. Okay? And your thin film equation remains the same. You just do it the way you will get it. If you have an elastomer field that is viscous elastic, the framework remains same. Once again, there is no difference, right? You are just changing the constitutive relation. You are changing the constitutive. Again, this is in terms of the displacement field. Earlier, in case of Newtonian, I have used the velocity field. Here I am using this as a displacement field. Here I am using as a displacement field, and framework remains same. Not only that, if you have a surface roughness, if you have a rough surface on which the film is resting, framework remains same. Only thing what changes here, say suppose if there is a surface roughness, what will be the changing factor? Changing factor will be z equal to 0 में uv 0 नहीं होगा. Z equal to a particular function में, say suppose you consider a kind of function, it will be 0. Right? And at the same time, here you may find that I have done a 3D nonlinear equation on a rough surface, the most generic form. So this is my x momentum equation. This is my y momentum equation. This is my z momentum equation. This is the continuity equation. This is the normal tangential balances at the interface. This is the normal balance. And you may see the kinematic equation only changes in case of a 3D situation, del h by del t, uh del h by del x, plus vh del h by del y, wh. Now, if I plug in everything, I'm going to get this as a kind of most generic form of a 3D, kinematic equation with surface roughnesses that are embedded. This is also an assignment. Please do it and submit. Okay, and the solution of this equation, you will find it here. This one. So what did we do? We started deriving the thin film kinematic equation. Then we put in a model framework. Then we enforced an order of magnitude analysis. And then from the order of magnitude analysis, we went for a Newtonian, okay, equation for the kinematic equation, then incompressible Hookean elastic, incompressible elastomer, and 3D nonlinear equation. I'm going to give one problem from here in the NSEM exam. Remember. Okay, one is from the Van der Waals forces, one is from the, because NSEM will be, offline. So these two will be there. One of them I will choose. So submit the assignment. There will be certain tricks of the trade. If you don't figure it out now, you will not be able to figure out in the exam. And subsequently, since open note, open book, the marks will be less. Okay. Yeah. Any question up to this point? Any question up to this point? You have any question? No questions? Understood everything?
Hello, sir.
Yeah.
Sir, sir, how that epsilon is decided? The sir, Z is 1. So, sir, what is epsilon? Can you explain that?
Which epsilon?
Sir,
this one?
The scaling, yes.
So
yes.
I said no, that say suppose you say that Z is 1 and W is very small. Okay, now if U is 1, then X has to be 1 by epsilon. This is the special signature. Yeah, the other argument comes from here. Say suppose I am looking for a system, say water-based system, right? What is my surface tension? It is 0.0728, right? What is the viscosity of water? What is the viscosity of water?
0.00.
0.001, right? And what is the film thickness? 100 nanometer means about 10 to the power minus 8, right? So if I calculate gamma by mu h, what is the number that is coming? Gamma is how much? 0. Let me just take the order of magnitude, 10 to the power minus 2, right? Mu is what? 10 to the power minus 3, right? And h is what? 10 to the power minus 8, right? So this is how much? How much is coming to be this?
10 to the power 9.
9.
10 to the power 8 to 10 to the power 9. I have given you a table. I've given you a table here. Okay. So 10 to the power 8 is gamma by mu h. What does it mean? That surface tension force is more predominant than the viscous force. Okay. Now let me calculate A by mu h cube. Van der Waals to viscous. So you will find, if I just plug in the values, you will get it 10 to the power minus 10 to the power 6. So Van der Waals force is again more predominant than the viscous force. Now I go for viscous to inertia. Mu by rho h square. These are all I'm cooking up non-dimensional numbers. So you will find this will come out to be 10 to the power 11. That means viscous force is more predominant than the inertial force. Right? Now you have a situation where surface tension force is predominant, where the Van der Waals forces are predominant, and these are predominant over mu, and viscous force is more predominant than the inertial forces. Okay. Under that sort of circumstances, say suppose, if you really want to look for the time scale, right? So time scale, you choose at what? You choose at the ratio of the surface tension force to the Van der Waals force, because surface tension will be stabilizing and Van der Waals force will be destabilizing. Because these are the two predominant forces you will see that will be there. Right? Now, if you plug in the values, you will see that in order to bring in the entire scaling towards 1, what you need to do, you need to empower these Van der Waals forces. Okay, you need to really play down. Say time means, viscous predominant means it will be fast at the same time slow, right? So rate should be fast, right? Of the order of magnitude of Z. Then X should be very large because high aspect ratio. There will be horizontal velocities, but there will be very less vertical velocity. So that's the way when it's all physical concepts you are bringing in. You are just cooking up different types of properties and looking at the situation before you are deciding. Say suppose if you are doing X by H0, this is typical order is 10 to the power 8. Right now, if you do H0 by X, so that is 10 to the power minus 8, and that is your epsilon. Now this epsilon you carry forward to the situation of what? To the situation of mu h by gamma. This is also epsilon. Mu h cube by A. This is also epsilon. Okay. Now, rho h square divided by mu. This is also epsilon. So you look at your equation. So all inertia epsilon. In viscous, some are there, some are not there. Some are there which are equivalent to this, some are not there. So inertia is 0. These are not there. Only this one is there. So you will find according to this analysis, viscous is the intermediate. Viscous is always there. It is the intermediate. It is the kinetic factor. Inertia is nowhere. Capillary and van der Waals forces are everywhere. So you will find the scaling has been done. Capillary and van der Waals forces are everywhere. Viscous is somewhere. Inertia is nowhere. Could I explain to your question?
Yes, sir. Thank you.
Right. So you have to look at the properties. From there, you have to conceptualize, because this you are doing because you are handicapped. You are unable to solve the equation. That's the reason why you are bringing in these arguments, in order to set up the equation in a manner so that you get a solution, and these solutions are working well at the practical level. So we'll start the electric field in the next class. Any other question you have? Otherwise we close. Vinod, just tell all the students who are not attending the classes now that I will be very severe in terms of their performance and all, in terms of checking and all these things, those who are not attending classes, because it will lead to a lot of problem later on. Okay, the attending the classes are mandatory. Just put up an email. Those who are not attending classes, I'm going to put F grade, if I see any more such activities. Okay, and you have announced, right? Next week we have classes on, I think Monday and Wednesday, correct?
Yes, sir. 14 and 16.
Yeah. So please announce, and attendance is mandatory. Okay. Yeah. Okay. Thank you so much. Bye bye.